Okay, so in the last example, we were kind of looking at the end behavior of polynomials. And from what we saw, polynomials have a very predictable end behavior. It really just boils down to looking at the leading coefficient and the degree of that polynomial to make a determination on what those limits at infinity are doing. Next, we're going to start looking at the end behavior of rational functions. So specifically, I want to focus on just the function f of x equals 1 over x squared. So this, if I were to plug 10 into this, well, let me back this up for a second. To analyze that end behavior, I want x to approach infinity and negative infinity. So I have this table here, which I'm going to use to kind of take a numerical approach and see what happens as x gets really, really big or really, really small. If I plug in x or 10 in here, 10 squared is 100, so I get 1/100th, which is, as a decimal, 0.01. Okay? If I plug a 100 in here, I would end up with 1 over 10,000. That's the same thing as 0.0001. Notice I picked up a couple extra zeros there. And there's sort of a pattern that appears here. Every time I plug in a new one of these, I'm going to pick up an extra 2 zeros. So 0.1234551, and then 0.1234567. There we go. So as you can see, these numbers are getting really, 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 really close to 0. That suggests to me that as x approaches infinity, this function is approaching 0. If I go over here and I look at what happens as x is approaching negative infinity, well, now I'm just plugging in the opposites of these numbers because the opposites would be negative. But because I'm squaring x, whether I'm plugging a positive 10 or a negative 10 into that expression, squaring it will make it come out positive regardless. And in fact, I would get all the same values even on this side of the table here. So again, I get this, 2, 3, that, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 6, 7, 1. So this appears to also be approaching 0. In this case, I would say that the limit as x approaches infinity of 1 over x squared is equal to 0, as is the limit as x approaches negative infinity of 1 over x squared. Okay, so that's numerically I'm showing that, but I can trust that this is actually what the limit is equal to. Now there's nothing special about the second power here. If I do 1 over x to any positive integer power, we're going to see the same thing happen. And I'm going to show that on the next page as kind of like a theorem or a result. But logically it makes sense that this is happening because we know that if we have 1 divided by a very, very large denominator, then we get a very, very small fraction. So the bigger this denominator gets, the smaller that fraction should be getting in the sense of approaching 0 this time. So that logically makes sense that we should be getting 0 as our limit there. Okay, here's that result that I stated. If n is a positive integer, then the limit as x goes to either infinity or negative infinity of 1 over x to the n. In both cases, we get 0. So that's great, but how do we deal with more complex or complicated rational expressions? Here I want to evaluate the limit as x goes to negative infinity of 4x cubed minus 7x over 8x cubed plus 10x squared minus 14. Well, there's a trick to these. So what I'm going to do is look throughout my numerator and throughout my denominator, and out of both of those, where can I find the absolute largest exponent? The largest exponent I'm seeing is 3. In fact, it's showing up in 2 locations, but of everything, it's 3. So that would be the degree of both the numerator and denominator polynomials. What I'm going to do is multiply this expression by 1 over x to that power, 1 over x cubed. Okay? The reason I'm going to do that is because it's going to take a lot of these terms in this polynomial and it's going to turn them into terms that look something like what I have up here. And now from this little result, we know how to deal with those types of limits. So if I did that, this is going to be the limit as x approaches infinity. Taking this 1 over x cubed and multiplying it to each of these terms, 4x cubed divided by x cubed is just 4. Okay, this x cubed in the denominator and that x cubed right there, those cancel each other. Minus 7x over x cubed. So I would have an x in a numerator and an x cubed in my denominator. I subtract exponents. That should give me 7 over x squared. Hopefully you can see why it comes out to that. Over. Now take this 1 over x cubed here, distribute it into all three of these terms. Once again, the x cubed in the denominator here cancels the x cubed right there, and I'm left with just 8. Plus 10x squared over x cubed. So the x squared will cancel with 2 of these x's down here, leaving me with 1 more x, giving me 10 over x there. And then finally, negative 14 times 1 over x cubed is just negative 14 over x cubed. Nothing is canceling, but I get that expression. Okay? Now, from our limit properties from the previous section, which I can also apply in this case here, this limit can be brought up into my numerator and denominator, at which point I can apply the limit to each term individually. And if you notice, 3 of these terms take this form. Now, they're not exactly this form. The limit as x approaches infinity of 1 over x to the n is 0. That has a 1 in the numerator. But even if I have some other constant, like a 7 or a 10 or a negative 14, we know from our limit properties that that constant can be pulled out to the front of that limit. So in other words, I'm going to write this off to the side. If I wanted to find the limit as x approaches infinity of 10 over x. Notice that's one of our terms, right? I can take that 10 and bring it out front. 10 times the limit as x approaches infinity of 1 over x, okay? But now this limit right here is the one that I know goes to 0 from this result right here. And regardless of the fact that this was a 10, it could have been 100 or a million or a negative pi, whatever it is, I'm still just taking a number and multiplying it to the 0 that I get here, becomes 0. Okay, so that term right there is going to go to 0. And by the same reasoning, so would these other two. So I'm going to indicate that by doing this. That goes to 0, that goes to 0, that goes to 0. What's left at this point? Well, I have the limit as x goes to infinity of just 4 over 8, which is 1/2, and being a constant, we know that the limit as x approaches anything of a constant function is just a constant. So simplifying that gives me 1/2. Okay? To see what that did, we can actually use something like Desmos to graph the function that we just found this limit for. We only found one of those limits at infinity. Oh, I think I put a negative in there. I meant for that to be a positive infinity, so I'm just going to put a positive there. This is the graph of that function. I plugged it into Desmos and I found this graph. Now, what we just found was the limit as x approaches infinity, which means graphically, what is the graph of our function doing as x gets really large? So as we go further and further to the right, what I'm seeing this curve do is it is appearing to level out. And it may be kind of hard to see from the video, but right here in the middle is a grid line at 1/2, and you can see that the function appears to be approaching that grid line. So that is kind of confirmation that our limit in the previous example really should have been 1/2 as opposed to infinity or negative infinity or just some other finite number. And that also helps us put the idea of limits at infinity into context when it comes to graphs. What a limit at infinity does, if it's finite, is it tells us where horizontal asymptotes live in a function. So this is a horizontal asymptote because it's a horizontal line, and my graph is approaching that line as x goes towards infinity. If x is approaching some, or if my function f of x is approaching some number as x goes towards negative infinity, that would also be a horizontal asymptote in its own right. These two parts of the curve do not have to approach the same thing as x is going to infinity or negative infinity. You can actually have two different horizontal asymptotes in a graph. We see that happen. Okay, so here is just a quick restating of what I just said. So if the limit as x goes to infinity of f of x is equal to L, or if the limit as x goes to negative infinity of f of x is equal to L, where L is finite, that part's important, then we say that the line y equals L is a horizontal asymptote of the graph. Okay, so let's, we'll revisit the topic of horizontal asymptotes a little bit later. Let's look at a couple more end behavior examples. Both of them are rational functions like we've already seen. Let's find the limit as x approaches infinity of this first function. And I'm going to do the same thing. I'm going to start by looking for the highest degree term in the entire rational expression, and that looks like it's this 5x to the 5th power. So using the same trick as before, that suggests that I should multiply this by 1 over x to the 5th over 1 over x to the 5th, like this. Okay? Paying attention to how things cancel and simplify and stuff like that, the 1 over x to the 5th will come over here, cancel completely with that x to the 5th, and leave me with just the 5. Minus x. When I divide that by the x to the 5th, it's going to distribute over here. I'm going to get minus 1 over x to the 4th. Plus 6x squared. That'll simplify to 6 over x squared. Cubed, sorry, x cubed. That's the numerator. Denominator, I'm going to take 1 over x to the 5th, multiply it in. That's going to become 3 over x squared plus 6x over x to the 6th, that would become, or x to the 5th, that becomes plus 6 over x to the 4th. Okay? Now the 5 is the only thing that doesn't have any x's in it. It's the only term that's missing an x. The other terms, these 4 here, are all of that form where I have a constant over x to some positive integer power. And from our previous result, we know that all of those go to 0. Okay? But here we have a problem. So my numerator is going to a positive number. It's going to 5. While my denominator is going to a negative, or sorry, not a negative, it's going to 0. So we know that when we have a non-zero number in our numerator and a 0 in our denominator, when we evaluate a limit like this, from the previous section, we know that that limit has to be either positive infinity or negative infinity. How do we determine which one? Well, again, because my rational function here is made up of polynomials, I would want to think what is happening to the sign of each polynomial as x approaches infinity. And remember, for polynomials, we only have to pay attention to the leading term, 5x to the 5th over 3x cubed. Okay? So in this case, because I'm dividing by 0 here, I can actually just focus on those leading terms right there and think this is going to be the same thing as the limit as x goes to infinity of just that 5x to the 5th over just that 3x cubed. If I simplify this, this is the limit as x goes to infinity of 5/3 x squared. I'm simplifying the x's there. Okay? This, from what we did on polynomials, I could say that this for sure would go to infinity because I have an even power or an even degree and a positive leading coefficient. That goes to infinity. All right, let's look at the other limit. What about the limit? I actually didn't want that equals there. What about the limit as x goes to negative infinity of our function? Well, I can do the same thing that I did before. I'm still multiplying the 1 over x to the 5th into everything, and so I'm still going to end up in the same place here. I still have 5 over 0, which is enough to tell me that this is going to go to either positive or negative infinity. And the question is, which one is it? So again, I look at just the leading terms for both polynomials and consider what would happen here. So once again, this is the same thing as the limit as x goes to negative infinity of just 5/3 x squared. Now in this case, again, we have that table for polynomials that we could use, or you could just reason your way through it. x we're understanding to be a negative number, very small negative number. And if I plug a negative number in for this, because this is a second power here, it's even, that's going to come out positive, and then I'm multiplying it to a positive. So I should be getting a positive infinity here as well. In both cases, my function is growing, it's going to positive infinity. Okay? Let's now look at this next example. So this time g of x is equal to x squared plus x plus 2. Same approach. It looks like, once again, my largest degree term is this x to the 5th, so I'm going to multiply by 1 over x to the 5th again. And just simplify as much as possible. So what we're looking at now is the limit as x approaches infinity of, let's see, so I'm going to get x squared over x to the 5th, that's 1 over x cubed, plus x over x to the 5th, that's 1 over x to the 4th, plus 2 over x to the 5th. So there, that's what I get from all three of those terms. I'm going to distribute the same thing here. X to the 5th over x to the 5th is just 1, minus 8x squared over x to the 5th. It becomes minus 8 over x cubed. Okay? As before, all of these terms that still have x to some positive integer in the denominator and a constant in the numerator will all go to 0 as x goes to positive infinity, which leaves me with just 0 in my numerator, 1 in my denominator, which is of course just 0. Okay? Now, if I'm having x go to negative infinity instead, so if I say the limit as x approaches negative infinity of the same thing here, in fact, I can even just call it g of x since that's what we labeled it, x going to either positive or negative infinity will not change the fact that this numerator is still going to 0 and my denominator is still going to 1. So in this case, I still get 0 even as x goes to negative infinity. And it's worth just quickly pointing out the three possible cases that we have seen with these rational functions. Going back to this one, when my degree of my numerator and my denominator was the same, so third power, sorry, my dog's making some noise. Then I ended up with a finite limit when I took the limit as x went to positive infinity. I would have gotten a finite limit if x was going to negative infinity as well. And not only is it finite, it's a non-zero number. Okay? In the case where the degree of my numerator, 5 in this case, was larger than the degree of my denominator, I got an infinite limit. Infinity in this case, another example might have come out to be a negative infinity, but the point was that it was an infinite limit. If I get the reverse of that, if the degree of my numerator is less than the degree of my denominator, I got 0. And again, that makes sense because the denominator is going to grow at a much faster rate than the numerator. It's going to overpower this function. Sorry, my dog is sneezing now. And it's going to go to 0. So we saw that across 3 examples, but that same pattern will always happen. I'm not going to write up like a table or something like we do with polynomials for predicting that, but it's a good thing to keep in the back of your mind. Okay. There's still plenty more to talk about. So we're going to shift from rational functions to a discussion of exponential functions. We looked at the graph of y equals e to the x at the beginning of this section. We've also looked at it at the first week of class. Just to return to that, it's right here. From the graph, we can really see what's going on with the end behavior of this function. As x goes to negative infinity, the function is approaching the x-axis, which really means that e to the x is approaching 0. It's coming, y is equal to 0 down here. So as the limit as x approaches negative infinity of e to the x is 0, we wrote that here. And then we also saw as x approaches infinity, positive infinity, this is growing without any bound. So that's approaching infinity. That is the case for the exponential function e to the x, but it's also generally true for any exponential function of this form, e to the nx, when n is just any positive integer. Okay, and it's very, very easy to see why that's the case. The graph would look very similar for any of those positive integers n. We would have the same end behavior. So again, as x approaches infinity, e to the nx will go to infinity. As x goes to negative infinity, e to the nx will go to 0, again, when n is a positive integer. So how can we use this to deal with limits of this type? We're looking at the end behavior for both of these functions. So starting with the limit as x approaches infinity of this function. For this guy, what I'm going to do is simplify it. I know that if I have an exponential function over another exponential function, I can simplify this into just a single exponential function, but I subtract these exponents. 3x minus negative 7x is just 10x. That puts this function exactly in this form, e to some integer times x, that integer being 10 in this case, positive integer. So this is the same thing as finding the limit as x approaches infinity of e to the 10x, and this tells me exactly what that should be. It should be infinity in this case, and if x is approaching negative infinity, e to the 10x, I should get negative, or not negative, sorry, I should get 0 in that case. So that is about as simple of a problem as I can give you in this section. Here, this is more complicated because it's not just a single exponential function divided by a single exponential function. In this case, we're looking at like almost like a polynomial, but instead of x's, I'm having e to the x's or e to different powers. So I wonder if we can try what we did before of raising these exponents to different powers. I'm sorry, not raising them to different powers, but kind of canceling and simplifying certain things. So I'm going to try multiplying this by 1 over e to the 4x and 1 over e to the 4x. And let's just see what happens when I do that. I'm going to now take the limit as x approaches infinity, and when I distribute this in 5 e to the 4x over e to the 4x, those exponentials will cancel and give me just 5, okay, minus, now e to the x over e to the 4x. We subtract exponents. X minus 4x is negative 3x, which is the same thing as 1 over e to the 3x, okay? Then I'm going to get plus 1 over e to the 4x. You should be able to see where that's coming from. Here, I'm going to distribute 1 over e to the 4x here. It's just going to cancel that e to the 4x and give me 2. Plus e to the 3x and e to the 4x, those will partially cancel. I'll get 6 over e to the x. Okay? Now think about what's going to be happening with these. So we know that as x approaches infinity, which is what's happening here, e to the nx is going to be going to infinity as well. But all of those e to the n x's, where I have positive integers in front of those x's, oh yeah, I was worried that 6 was in the wrong place, but I put that in the right place. All of those denominators will be going to infinity. And we know that as the denominator of a fraction gets really, really big, if the numerator is not changing, if it's constant, then the fraction itself is going to shrink towards 0. So because we're getting really large denominators here, then these reciprocals, or these 1 over or 6 over those exponential functions, those are all going to 0 in this case. Okay? All that leaves me with here is 5 over 2. The limit as x approaches infinity of 5 halves. And being a constant function, it doesn't matter what x is approaching, that only comes out to that constant. So we get 5 halves right there. Okay? So that's one down. What about the limit as x goes to negative infinity? So again, we're looking at this function with all of these exponentials up here, but thinking about what it would mean for x to go to negative infinity. The function e to the nx is going to go to 0. And that's not super helpful if I have this rational, or this expression in this form that I put it in right here. Because if these denominators are all going to 0, then that means the fraction itself is actually getting very, very large in the positive direction or very, very small in the negative direction, depending on whether I have a plus or a minus in front of it. That's not going to be helpful. I don't know how to interpret that here. So instead, what I want to do is think about what would happen as x gets very, very small to all of the terms as they are already written there. 5 e to the 4x minus e to the x plus 1 over 2e to the 4x plus 6e to the 3x. Okay, so what we know is that each of these individual terms, e to the 4x, e to the 3x, so on and so forth, those will all go to 0 as x goes to negative infinity, which is what x is doing. So there was no need to multiply by 1 over e to the 4x. As written, all of the exponential functions here are going to go to 0. Okay? With that in mind, what is left in this limit? Well, I have 1 over 0, and that's undefined. So clearly in this case, the limit does not exist, and we do want to specify how it is failing to exist. So I'm going to say it's got to be either positive or negative infinity, and in this case, I can actually say it is positive infinity. The reason I know that is before crossing these all off and making these all zeros, I know that my numerator is going to 1, which is a positive number. My denominator, even though it's going to 0, it's going to be positive the entire way as it approaches 0, because exponential functions can only be positive, right? Remember, that's part of the range of an exponential function. They only have positive outputs. So this denominator will only ever be positive. That gives me positive over positive, so I'm getting an infinity as opposed to negative infinity. Okay? All right. I think we'll save this discussion here of logarithmic functions for the next video.